So now let's take another example. So to do another example, I have to define another problem. The problem that I will define is set partition. Given a set S of integers, determine if S can be partitioned into two subsets with equal sums. Now, what problem does this remind you of? Subset sum. Yeah, it's very similar, very close. That's why you know when you do NP-completeness proofs, you try to find a problem that is similar or close. Okay. Now let's take an example. Example 2, 3, 4, 2, 3, 4, 7. Well, let's first take 2, 3, 4, 8, 1. So can you partition this into two subsets with equal sums? Yes. So the answer here is yes. I can partition it into 2, 3, 4, and 8, 1. So I managed to partition this into two subsets with equal sums. So this sums to 9 and this sums to 9. Okay? Another example is 2, 3, 4, 7. So in this case, can you partition it into two subsets with equal sums? No, you will not, because this is the largest number, so these will not give you 7. Yeah, 2 and 7 will give you 9. You will not find a way to partition this into two subsets. So the answer is no. Again, you know, this is another NP-complete problem. So if it doesn't have a polynomial time solution, so you know, in order to determine if there is if you can partition it into two subsets with equal sums, what will you have to do in brute force? So you should consider all subsets. So you look into all subsets and you see if the sum of the complement of that subset is equal. So you consider every subset, and for every subset you check if the sum of elements in that subset is equal to the sum of elements in the complement of that subset.
So we cannot take subsets which has only one element?
Subsets that have one element?
Yeah.
Yes.
Like, a set with only element 7 is a subset of this, right?
Okay.
So 4 and 3 and 7 will have...
But this is not a partition. A partition will have to use all elements. So a partition by definition has to use all elements, and each element can appear in only one partition, right? So you cannot skip elements. You have to use all of them. Okay? So this is set partition. Now, let's see if we can prove that this problem is, well, let's try to prove that if we know that this problem is NP-complete, we can prove that subset sum is NP complete. So now, assuming that, or let's write it here. We're done with this. Now, assuming that, of course, both of them are known to be NP complete, but we're doing an exercise. Okay, we're doing an exercise to show reductions. Assuming that set partition is known to be NP complete, prove that subset sum is NP complete. Now remember, don't forget the first condition. Okay, don't forget the first condition. So number one, you have to show that the problem that you are trying to prove is NP complete, which is in this case subset sum. You have to show that it's verifiable in polynomial time. So subset sum is verifiable in polynomial time. And we have, fill in the blanks here. So we said how to verify subset sum in polynomial time. Verifying subset sum means that if someone gives you a subset, so the problem is you are given a set and a target. So if someone gives you a subset and says that I claim that this is a correct solution, you can easily verify that it's a correct solution by checking that the elements that they are giving you are in the set. So this can be done in polynomial time. And then summing these elements and see if the sum is equal to the target. Okay. Now the more interesting step is verifying or reducing. Now in which direction do we need the reduction? So in which direction should the reduction go? From subset sum to set partition, or from partition to subset sum?
Set sum to set partition.
So we go from the known to the one to be proven, or from the one to be proven to the known?
One to be proven to.
Yeah. So you go from the known, right? It's this. So the one that we are trying to prove should be here. The one that is known should be here. So we're trying to prove that this is greater. So we're trying to prove subset sum. So subset sum should be here. And the known, the one that is assumed to be known, the set partition, should be on the left-hand side. Set partition. Again, this is the one to be proven. You have to prove that it's greater than or equal to the known one in terms of difficulty. Now I assume that I have a solver for which one? I assume that I have a solver for this. I assume that I have a solver for this, and that any instance of set partition, I can reduce it to an instance of subset sum. So assume that you have a solver for subset sum. Now this solver for subset sum, what does it take? It takes a set, and it takes a target, and it gives you yes, no. So this is subset sum solver. So now how can I employ it to solve the set partition? So the examples are 2, 3, 4, 2, 3, 4, 1, 8. This should give me yes. And if I give it 2, 3, 4, 7, it should tell me no. So how do I use a subset sum solver to solve this problem? So what set and what target should I give it?
We know that the target will be the total sum upon 2 of the set
The total sum
by 2.
divided by 2. Exactly. So this is very obvious. You are trying to partition this. So your target is going to be the sum divided by 2. So you just give it here, what's the sum? 18. So you give it 9. Because the sum of these items is 18. So you give it the target equals sum divided by 2. And S is just the given set. So, well, let's use different, let's use just different symbols. So if, let's call it S prime. So this is the given set. So just use the same set. Okay. S equals given set. And that will, instead of trying to introduce notation, S equals the given set. And T equals the sum divided by 2. And that's it, right? So it's very easy to see how we can, I give you a solver that you give it any target you want, and it tells you if there is a sum of this target or not. So if you want to split this set into 2 equal parts, you just give it a target as half the sum. And then it will tell you if it can be split in half or not. Okay? Now what is trickier is to solve the problem in the other direction. Okay. So any questions on this first? Okay, now to solve the problem in the other direction, now assuming that subset sum is known to be NP-complete, prove that set partition is NP-complete. Okay, so now you need to say that set partition is verifiable in polynomial time. So now who can describe how can we verify set partition? What does verifying set partition mean?
Both the sum of the elements in both the subsets are same.
Yeah, exactly. So a proposed solution to set partition is 2 subsets. Someone gives you 2 subsets. So you first check that the sum of elements in both subsets are equal, but you also have to check what?
Whether they belong to the actual set or
that all the elements belong to the elements of the original set, and you also need to verify that there is the intersection of the 2 subsets is phi, is empty. They do not intersect, right? And you also need to verify what?
their union is equal to the actual set.
Yeah, exactly. Yeah, exactly. So you need to verify that it's a valid partition, which means their union is equal to the original set, and their intersection is phi, the empty set, and you need to verify that the sums are equal. So, and you can do this in polynomial time, right? Everything that we have mentioned can be done in polynomial time. Now we need a reduction from subset sum to set partition. Subset sum to set partition. So now we assume that, so does this look harder or easier?
Easy.
Easier? So, okay, so how do you do it? So So tell us how to do it then. I don't think it's easier. For me, it's harder. Okay, it's harder because, which of these two problems looks harder on the surface? When you look at these two problems, which one looks more general? Yeah, subset sum looks more general. It's clear. Clearly, set partition is clearly a special case of subset sum. So it was very easy to see how to use a subset sum solver to solve set partition, because set partition is clearly a special case of subset sum. A special case in which the target is the sum divided by 2. But now you are assuming that you have a solver for set partition. And the solver for set partition takes only S as input. So somehow you have to encode the target, because an instance of subset sum will have a set and a target. So somehow you have to encode the target here and employ this solver for set partition to solve subset sum. So for an example, let's use this, and let's say our target is equals 12. So use this example. You have this set and your target is 12. So should the solver say yes or no?
Yes.
Should say yes, because you have 4 and 8. So it should say yes. How do you make it say yes? How do you make this say yes? It doesn't allow you, it doesn't take the 12. You can only input a set, and it tells you if you can split it in half or not. That's what set partition does. You give it a set, and it tells you if you can split it or not. How can you use this to solve this problem, which has, which takes two parameters, the set and the target? Yes. Yes.
We can add one more element to the set, which is the total of the set minus the target value.
Okay. Okay, good. So the target here is 12. And you want to add an additional item, which is the sum minus target.
Yeah.
Sum minus target. So what's the sum? Sum is 12 plus 5, so 17. 17 minus target, 17 minus 12 is 17 minus 12 is 5. So you want to add a 5. So you add a 5. Okay. So will it be able to split it in half then? So you're close. So it's not quite. So you add an element. But how do you select the value of the element such that if this solver manages to split it in half, it will give you the target that you want? So if this manages to split it in half, it should give you the target that you want. So what should the half be?
2 into target minus the sum of the set.
Okay, yeah. If the half, let the half be your target, because this is just a splitter. It tells you if it's splittable in half or not. So now, if you want the 12 to be the sum of one of the partitions, let it or force it to have another 12. So to make it have another 12, then you add another element that is equal to sum 2 times sum minus target. Twice the sum minus the target. So twice the sum is, what's the sum? The sum is 12 plus 12 plus 5.
17.
Yeah, 17. Sorry, it's not. Yeah, it's not 2 sum minus target. So you want the whole thing. You want the whole thing to be equal to 2 times the target. So you want this, the whole sum, you want it to be 24, because you want this 12. So you want the whole sum to be 24. So it's 24.
Sum minus target minus the rest of the elements in the set.
Okay, so it's 2 times the target, which is 24, minus, so what do you need to add?
Rest of the elements.
Yeah, the rest of the elements, which is minus 5. Or, in fact, well, the target, 12 minus, sorry,
2 into target minus 7.
okay, so what you want here, you want the total sum to be 24, and that 24 should include the 12 and the 2 and the 3. So it's 24 minus 12 plus 2 plus 3, and this is 17. Yeah, so this is going to be 17. So 24 minus 17, that's 8. Yeah. So it's, if you
It's 7.
7.
sorry, yeah, 24 minus 17 is 7. Sorry. Okay, so if you add a 7, then if you add a 7, then the 7 plus the 2 plus the 3 is going to give you a 12, and you have 4 and 8 equal to 12. Okay, so now 7 plus 2 plus 3 is 12, and 4 and 8 is 12. So if you give it this set, and if this solver manages to split it in half, each half will be the 12 that you are looking for, the target that you are looking for. Okay, so this is in fact 2 times the target minus the sum of elements. So it's 2 times target minus sum of elements minus sum. But in fact this will be the case if your target is greater than half the sum. If your target is not greater than half the sum, well, in fact, you can always assume without any loss of generality that your target is greater than half the sum. Why? You can always assume that your target is greater than half the sum without losing generality.
Because both sets have equal sum of weights, that's why.
Yeah, well, because if your target is 12, solving the problem for target 12 is equivalent to solving the problem with target 5 in this case, because it's looking for a subset that sums to 12 is equivalent to the problem of looking for a subset of size 5. So for every target, you can also look for the complement of that, right? So if the target is not already greater than half, you look for the target. So if your original target was 5, I can do 12, because I know that the sum is 17. 17 minus 12 is 5. Okay, so in this case, let add an element an additional element, an element with value equal to 2 times target minus sum. or construct S prime. You can say construct S prime. S prime equals S union A, where A union A, where A equals 2 times target minus sum. Then S prime can be partitioned if and only if S has a sum, a subset that sums to T. Okay. Okay, so now this is, this reduction was trickier, right, than the reduction. Now, it was trickier because on the surface, subset sum looks more general. But in fact, we have proven that they are both at the same level of difficulty. We were able to do the reduction in both directions. We were able to reduce subset sum to set partition and to reduce set partition to subset sum. So we managed to do the reduction in both directions, which means that they are both at the same level of difficulty. In fact, all NP-complete problems are at the same level of difficulty, but within a polynomial. So it's so the difference in the complexity of the algorithm that can solve one problem. The algorithm that can solve one problem can differ from the algorithm that can solve another NP-complete problem by polynomial only, not by exponential or factorial. Okay, any questions on this? Okay, so that was the second example, which actually included 2 examples.